Alright, so today we're doing Chapter 10 in the Barron's book, which is Chemical Equilibrium. I put equilibria, that's just a plural, don't worry about it. Anyways, this is for me when chemistry started getting a little harder, like in retrospect. Seems hard all year, I'm sure, but next couple units are probably going to be a little tougher than the other ones. So hang in there. Alright, so first off, what is equilibrium? Well, equilibrium, I have covered it briefly before in other videos, but the main point is it's when a chemical reaction is constantly going in both directions. So products are always being turned into reactants, and reactants always are being turned into products. So that's this symbol right here, that's the equilibrium symbol. That's how you know it is in equilibrium. And the first thing our book will want us to do, this is the real foundation of almost all of this unit, is find the equilibrium expression. Well, let's talk about what that is. So each equilibrium has a part or a number called the equilibrium constant. This is again a K, not to be confused with Kelvin, so sometimes there's Kc next to it. I don't know, it depends, but usually it's just K. You'll see later ones that are like Kp or Ka, Kf, Kb, Kd. This is all other stuff, like Ksp is the equilibrium for a solubility product. So don't worry about it for now. All you need to know is K or Kc. But so here's how I'm going to write the expression first, and then I'll explain it. But pretty much you have the constant, the equilibrium constant, is equal to P to the P. It's for this reaction up here, by the way. This guy turns into this PP and N over A B B. Alright. At first, this guy looks kind of scary to learn, but it's not too bad. Well, first off, this is the equilibrium expression for the equation written like this. If it was flipped, with the P's and N on this side and the A's and B's on that side, then the fraction would be flipped also. The product always goes on the top. Always. And the reactants always go on the bottom. Now, next thing we see is, so these values up here, these are coefficients, right, to how much of chemical. So that might be like 3CH4. So 3 would be lowercase a and CH4 would be capital A. That's just an example. Who knows what's really happening in your example or your own equilibrium. Anyways, that's an example of what it could be. So then you'd plug in the CH4 down here and the A up there. And the brackets, if you remember from concentration or from the solutions unit, the brackets represent concentration. So it's moles per liter, right? We all know concentration. So what it is this equation is the concentration of product to the power of its coefficient times the concentration of the other product, if there is one. I mean, this could go on ... and ... right, for all of these. But it's just concentration to the power of its coefficient. And then that will give you the equilibrium constant. So later, I mean, all you need to know right in this slide is how to set up the equilibrium expression. But if they tell you what the equilibrium expression is, you can use this equation to solve for certain concentrations, especially if you have the chemical equations already. So pretty important for this chapter. Learn this. It's a big deal. Alright, so I'm going to do an example of writing an equilibrium expression for you. So first step, right, is Kc. We all know equals the equilibrium constant. Alright, so what we're going to do next, right, product, so concentration of product 1 to the coefficient of product 1 times concentration product 2 to the power of the coefficient of product 2 divided by, I can do this in a different color, divided by concentration product, or concentration reactant 1, which in this case is butane, I think. No, propane. I apologize. That's awful. And then, whoops, made a little mistake. No, 3 there, right? There's an imaginary 1 there, so imaginary 1 there. And then concentration product to the power of the coefficient. So that's how that equilibrium expression would look. Not too hard, right? And if this was an equation we were solving for stuff, they'd give us the concentration of some of these, and we could, and maybe that guy, and we could plug it in to solve for a missing one. So yeah, there you go. Not too bad yet. Alright, so I'm going to do another example and then show you how to reverse it, which is something I briefly touched on at the beginning, but we will go over it right now. So this first equation, right, you probably had some practice by now. You get Kc, equilibrium constant, equals product, right? So we're going to have concentration SO3, 2, and then product, or reactant, so O2, SO2, 2. Alright. So now, oh, my bad, that should be equilibrium. Did I do that on the last slide? I hope not. No, I don't think I did. Alright, anyways, so that's the equilibrium expression, right? Well, what if we wanted to reverse this equilibrium? Well, we can also write it as 2SO3 turns into O2 plus 2SO2. And so what would our new expression be? Well, we're going to call this K prime C, and this one is going to equal, we're going to call it K prime C just so we can differentiate it and like tell the difference between it and this one, right? We don't want to get confused. So this one is going to be, what are our products now? Oxygen and SO2, right? So it's going to be concentration oxygen times concentration sulfur dioxide to the second power over, boom, SO3 second. So there you go. And as you can see, K prime is the reciprocal of Kc. So that's all you need to really know about reversing a chemical equation. I mean, you can always solve that like by doing them both out, right, like that way, but you might get a test question that tells you what the equilibrium constant of this one is and asks you what this one is, and then you should know that it is the reciprocal. So there you go. Alright, the book here talks about multiplying or dividing coefficients by a constant. Never seen it before, never used it, but let's imagine we have our O2, 2SO2 equilibrium with 2SO3. Well, let's say we want to multiply this by 2. Well, the book does 3, I'll just do 3. By 3. Well, it's going to make 3O2 plus 6 SO2 turns... let me fix that, it's ugly. I'll even make it that way. And then 6SO3. Alright, so that's what that turns into. Now, if we find Kc, that's K double prime, just so we can differentiate it more, we'll call products, right? Sulfur SO3, or sulfate, to 2 over O2 to the power 3 SO2 6. That one should be 6 also. That was a bad mistake. Alright, anyways, so this is our K prime, and we can, if you remember, our K from last time was SO3 2 over O2 SO2 2. So we can see from here that this guy cubed equals K double prime. So K cubed equals K double prime. So if you multiply or divide by a coefficient, that coefficient is going to become the power by which the original Kc is multiplied. So there you have it. I've never had to use this relationship again, so I won't spend too much time worrying about it, and you can just solve it out really fast by just making your new equation and turning it into your equilibrium constant or your equilibrium expression. So I don't think it's too important to memorize, but there you have it. Alright, so this next thing is called adding chemical reactions, and this one is a little more common because later, or now maybe, it depends on what order your chemistry chapters went in, but you'll see reactions that they're not one-step reactions. They don't go right from one chemical to another. They go in 2 parts, or 2 or 3 parts usually, but then usually when you're dealing with the normal reaction, you just deal with one step. So if we keep using this one right here, well, you can see you start with sulfur and oxygen, and then you make sulfur dioxide before you make your sulfate, I think it is. So that's a 2-step reaction, right? You got to change sulfur, and then you got to combine it with oxygen again to get your final product. So I'll do this guy in green and this guy in red so we can keep them apart. So first, the green one, products first, right? Sure, by now, that's a 2. You should all get pretty sick of this. Pretty repetitive, right? So let's go through that pretty fast. And then we'll do the one in red. Wait, hold on. And this one's going to be K1. That's step 1. And so this one we're going to do... that was a mistake to draw. Boom. It's going to be SO3 2 over SO2. Alright. So that was that real fast. So now we're going to multiply these together, and this is the rule to remember. Well, I guess we can do it like this. We can see that 2 sulfur, right, and then 3 oxygen. It's a 2-step reaction, but since that's a product, that one's used there. You see that those 2 things make 2 SO3, so we can write a final one in purple for SO3 2 over S2 O2 3. This is going to be KO for K overall. Put OV so you don't think it's K naught. Alright, so now you may or may not be able to just see this on your own, but this is K1 times K2 makes K overall. See? So if we multiply these out, SO2, they're going to cancel, right? And then you're going to have a 1 there, a 1 there, and then 1 times SO3, 2, you get SO3, 2, and then S2 times 1, you get your S2, and then the O2 to the second times O2, give you O2 to the third. So as you can see, these are the same. K1 times K2 equals K overall. So this is a rule that you will need to know. I recommend memorizing it, because when you do multiple part reactions, you need to know what the K overall is. You might be asked in a multiple choice if the K for one reaction is this and the K for the second reaction. Like if I gave you that K and I gave you that K, and I asked you what was the K for this total reaction and the equilibrium constant, you should be able to tell me, because that rule. So that's one you need to know. Alright, now we're going to do one where we actually find the value of K. So yeah, I don't think this part is too hard. They just give you the data, and that should be a 2. They just give you the data on concentrations, and then you pretty much just plug it into your equilibrium expression, which we've done a fair amount of. So I'm only going to do one example for this. Again, our Kc is going to equal SO3 2 over O2 SO2 2. Alright, so that's our equilibrium constant, and let's say at equilibrium, I tell you O2 is 2 times 10 negative 8 mole. You will usually be dealing with pretty small concentrations, I would say, as a general rule. So if you get something like 8,000 moles per liter, it's probably wrong. Try it again. And I tell you that the concentration of sulfur dioxide is 3.4 times 10 to the negative 9. I told you that SO3 was 0.971. Well, we just plug this into our equation, solve for Kc. So our Kc equation will look like Kc equals 0.971 squared over 3.4 times 10 to the negative 4th squared times 2 times 10 to the negative 8th. So as you can see, this one takes up a lot of space, but when you plug this into your calculator, you will get that K is 4.2 times 10 to the 24. Now, it is okay to have a large equilibrium constant. I would say, as a general rule, you won't unless the concentration of products is, like in this case, much greater than these people. Or, I'm sorry, not these people, these the reactants, but I mean, you can just estimate just from this information, hey, product is a lot bigger than reactant, so K is going to be huge. Well, it's not always going to be the case, but if this was a lot smaller of a number and we got this answer, I would think something was wrong. So just keep it on your concentrations, get a feel for what your answer should be ballpark based on your K value, so you're not making silly errors. But there you go. Not super hard, just mostly plugging in data. Alright, well, right now we're going to talk a little bit about equilibrium expressions and its reaction to spontaneous reactions. Probably not too sure what spontaneous reactions means at this point, because the thermodynamics chapter is later, but if you do not know what it is, a spontaneous reaction is a reaction that'll occur in the given conditions by itself. Like, you don't need to add energy or anything. Well, if they give us... Alright, well, here's just the general rule. If if I could write, if Kc is greater than 1, spontaneous. Why? Well, if Kc is 1, that means there's about an equal concentration of products as there is reactants. Well, that means that it's going to be just equally happening forwards as it is backwards. But if the reaction's happening more forwards, that means it's spontaneous. So, as you can probably guess, Kc is less than 1, it's non-spontaneous. In the book, on page 358, there's a good 2 paragraphs explaining this. Personally, this is all I think you need to know about the matter, especially because almost all of these spontaneous/non-spontaneous reaction questions on your AP exam will be having to deal with thermochemistry and whether it's endothermic, exothermic, and all those thermodynamic terms that you'll learn about later. So for now, I just worry about this. Keep it simple, right? If you want to know more, again, in the book, on the internet, go somewhere. Right here, personal advice from an AP exam taker. This is all you need. Alright, so now we're going to learn about something called the reaction quotient. Alright, so in this, well, for always, it is called Q, and as you know, that's Kc. Alright, well, up till now we've had the expressions, the equilibrium expressions dealing with Kc. That's because we knew those expressions were in equilibrium. Well, sometimes they're not in equilibrium, and like if I have a ton of SO3 and not a lot of, that's a bad example. We saw that there would be a lot more SO3. Or if I have a ton of oxygen and sulfur dioxide but very little SO3, well, we know the Kc is pretty high, so we can, and in this case, from the way I described it, the Q would be pretty low. So it's probably, the reaction will shift towards the product side and make a ton of SO3 so that it could reach equilibrium. Well, the reaction quotient, if it's not at equilibrium, that's what the equation makes. So this would be SO3 2 over O2 and then SO2. Looks very familiar, right? It's the same equation. This is just not at equilibrium. So there's 4 things you should know about Q and and Kc, like the relation. First, if Q does not change with time, lowercase t for time, sorry, capital T is temp. That's probably an extra comma, not really important, but then Q equals Kc equals EQ. So this means that if Q is not changing as time goes on, that means the reaction has reached equilibrium. There's no, everything's at the concentration and will be at equilibrium, which means Q has reached Kc, which means it is in equilibrium. Alright, number 2, very related. If Q equals Kc, it is in equilibrium. Just talked about that. Q is the value given to the equilibrium expression when it's not certainly, like 100% certain that it is in equilibrium. So, yeah. But if it is Kc, then it is in equilibrium. Alright, now these are big ones. If Q is less than Kc, which this is something I talked about already, the reaction will move forward. So this means that it will favor the product side. So that means that normally, right, we have an equilibrium. I'll try to give you a visual. Let's say we have the O2 plus SO2 makes 2SO3. Well, if we have a ton on this side, a lot, and we have a little over here, our reaction wants to reach equilibrium. So it's going to make a lot of this so that you can have the proper amount on each side. So if I have a different color, the way I would visualize this, saying it's favoring the product side, is 2SO2 big arrow that way, right? A lot of it is turning to SO3, and not so much is turning back into reactants, because you're trying to make a ton of product so it can reach equilibrium. So this is called favoring the product side, or shifting in the product direction, or just going in forward direction, shift to the product side. It's a lot of things you can call it, but all you need to know really is that it's making a ton of product. Alright, now the last thing is that this goes hand in hand with that. If Q is greater than K, then reaction goes backwards to reach equilibrium. So this would be, if I can erase something, let's see. Oh, not that one. There. Alright, this would be like we have our O2 and we have our SO2, and there's just too much SO3, then maybe makes a ton that way and not so much that way, so it can reach equilibrium. So there you have it. That is K, introduction to K, which is reaction quotient, and introduction to Q. I usually use Q instead of KC for most of my work because you usually don't know for certain if it's a equilibrium or not. But there you go, Q and KC. Alright, now we're going to go over a very important concept called iceboxing. So in the book it is called the equilibrium table. That's stupid. The name icebox lets you remember what's in it. The I stands for initial, so we're going to set up our thing. Alright, here we have reaction. Let's use just the one we've been doing. O2 plus 2 SO2 makes 2 SO3. Alright. Boom, boom. So the first thing, the I in I stands for initial concentration. So let's say you have, I don't know, 0.2 mole oxygen, 0.2 mole SO2, and you want to see what happens when it reaches equilibrium. Well, and let's say we have 0 of our SO3. We want to see how much we'll have when we reach equilibrium. Well, the C in icebox stands for change. So we don't know how much is changing by yet, so we'll do plus, no, well, we're going to be losing this, right, because we know it needs to favor the product. Minus x, you get plus x. In fact, this one actually gets minus 2x, and this one gets plus 2x because those guys right there. Alright, and now the E stands for equilibrium. Well, this is I'll just do it like this. So at first we have 2.2 minus x for this one. So we're going to have 0.2 minus 2x. So we're going to have 2x for our answer. Now we want to solve for x. Well, it depends on what we're given. If we're given Kc, right, as a distinct value, then we can set up our equation like 2x squared over 0.2 minus x times 0.2 minus x squared, right? And then we solve for x. Pretty sloppy. I'm sure I'll do an example of this later, and I'll show you how to use something called the solve function on your graphing calculator. I'll try to explain it in words at least. But yeah, and you just plug in the data and it solves for x for you, so you don't have to do all the nasty algebra that's involved here. But the other thing that might happen is they might tell you, oh, at equilibrium we measured that oxygen had 0.1 mole. So then you know x here is equal to 0.1, and you just plug in, oh, now I have no sulfur dioxide, and 1 mole of oxygen and 2 moles of SO3. So that's probably not a realistic equilibrium, but if that was our measured amount, then we would know. That's what we would know. So there you go. That is the icebox. I'm sure I'll do a nice real example in a minute. Alright, this video is getting a bit long, so this is going to be the last slide on here, and it's going to be a nasty one, so pay attention. It's going to be an icebox example. So, let's take our reaction. That was not a big enough box, was it? I'll just do it as I go. Alright, let's take our reaction from before. O2 plus 2SO3 turns to 2SO3. So that's a 2. I keep doing that. Alright. As we know, I is initial, C change, E is EQ. Alright, so let's say originally, like I said before, we have 0.2 oxygen. Let's say we have 0.3 SO2. You know what? Let me just, there we go. Say 0.2 moles, or molarity, which is moles per liter, 0.2 moles per liter oxygen. Let's say we have 0.3 moles per liter SO2, and let's say we have 0 moles per liter of SO3, like I said before. Alright, now let's get a new color. So, right, we're going to have our minus x, right? We're going to have 0.3 minus 2x, and you get to be plus 2x. So at equilibrium, that's what we're going to have, right? We're going to, I guess the minus x would be the change, minus 2x plus 2x. So at equilibrium, we would have 0.2 minus x, 0.3 minus 2x, and 2x. So first we're going to set up our equilibrium expression. It's going to go a little something like this. 2x, remember there's 2 SO3, so we're going to have squared over oxygen, which is 0.2 minus x, and then sulfur dioxide, which is going to be 0.3 minus 2x squared, because there's 2 of that too. Alright, let's say our Kc is 0.1. Now I don't want to do that. I'm going to make it 0.01. I don't know exactly how it's going to turn out. I haven't done this yet, but so I'm going to tell you how to do something on your calculator. You're going to love it. Alright. It's kind of hard to get used to at first, but bear with me because I'm going to do this step by step with you. So, first we're going to set up our equation here as 2x squared over 0.2 minus x, and then 0.3 minus 2x squared. Alright, now that's the first chunk, right? Well, we're going to do that whole thing minus, you know what, let me move it so we can see things. Alright, we're just going to move on. I'm going to move it off screen because we're only using this chunk now, right? You can rewind if you want to see the other chunk. Alright, so that's, here, I'll cross it out and we'll just 0.3 minus 2x squared, right? So that's the equilibrium expression minus our Kc, which, remember, was 0.01. So we're going to do that minus our 0.01 equals 0, right? We took 0.01 away from each side. So what we're going to do here is turn on our graphing calculators. You're going to need a graphing calculator for this, which you should have already for chemistry. You're going to hit second, and then catalog, which is on the 0. So hit second, and then, which is the yellow button, the top left corner, and then the 0. So this will bring you to catalog, and you're going to hit the, I should put arrows because we're going to use commas later. Alright, and then now you're going to hit the LN button. I'm sorry, the LN button, because that stands for the letter S. You'll see it in green above the LN button. If you're having trouble like not thinking like that, just look for the green letter S written on the key, or on the calculator, not on the button. I'll take you down to the S section, solve. So now what you're going to do is scroll down to solve. It's alphabetical, so it's going to be a second. Now you have solved. So now you need to set up your equation in your calculator, like so your thing should take you back to the home screen. It should say solve, and then you should put, I always say go excess parentheses, because I even put 3, right? I mean, having to insert them at the end is no fun. So then 2x squared, and then divided by whichever way that slash goes, and the parenthesis 0.2 minus x, parenthesis, we should have 2 there, so we can do 2, and then we can do our 0.3 minus 2x squared, whoops, that is parenthesis, then we're squaring the whole thing, right? And then here's your end parenthesis, and minus 0.01 end parenthesis. Now, this is where it gets kind of nasty. You're going to hit the comma button on your calculator. It's between the x squared and one of the parenthesis buttons. You're going to hit comma x. That's telling your calculator you're looking for the variable x. Comma 0. That's telling your calculator that this expression we made equals 0. And then comma. Now you're going to put in brackets, which is the second, and then hit the parenthesis button. You're going to tell your calculator what x can be. So I usually just put like 0, comma. So you're going to have 0, comma, and then your end value, which I usually put like 1 or so. I mean, just because that's a reasonable number. Then your end bracket. Sorry, that's an ugly bracket. And then you're going to hit, I wouldn't do the end parenthesis. I think it should be fine. Alright, then you hit enter on your calculator, and it'll think for a minute, right? And it'll spit out an answer, which in this case should look like 0.021. So that'll tell you that's equal to x. So if we look back at our beginning thing, we can see that 2x, so they might ask you how much SO3 is there now? It would be 2 times that number, right? So it would be 0.0042. I'm going to ask you how much sulfur or sulfur dioxide and oxygen are left. Well, this number is so tiny, it's like negligible. So, I mean, you could write like the 0.3 minus 0.004, which would be something like 0.296. I mean, that's not super negligible, so I guess I'd do that one. 0.2996 even, I think. So I might do that one. It depends what the significant digits are, but sometimes you'll get a really tiny x, and then you won't even have to, like, the difference in the reactants or the product will be negligible, and you won't even see it in your answer. But that would be how much SO3 there was if the Kc did in fact equal 0.01. So there you go. That is the Icebox. Now I know, doozy of a slide. Watch it a few times. Make sure you get it. And I cannot stress the importance of the calculator part enough. go over that as many times as you can until you can just pretty much, you can do it without instruction, as long as you know what the stuff for your equation or your expression is, because that is an invaluable tool on your final and on your AP exam, and really just algebra general. I mean, how handy is that? But I'm going to end the video now, and then part 2 will pick up where this one leaves off, maybe with another example, maybe not, we'll see. But there you go. That's iceboxing and little calculator tutorial.